Here's lesson 3 of the trig geometry unit. In this lesson, let me teach you how to solve trig equations. And to solve trig equations, you're going to have to learn how to identify different angles that have the same trig ratio. Before we do that, let me remind you about how we're going to interpret an angle theta. An angle theta, what it does is it rotates a terminal arm around a circle that is centered at the origin. And if we know where that terminal arm intersects that circle, we would be able to write the sine, cos, and tan ratios for that angle theta in terms of the x-coordinate and the y-coordinate of where it intersects the circle and the radius of the circle. Using SOHCAHTOA, if I want sine of theta, sine is opposite over hypotenuse, so from theta, I would do opposite, which is y, over hypotenuse, which is the radius. So sine of theta is y divided by the radius. Cos of theta, cosine is adjacent over hypotenuse, so from theta, adjacent is x, hypotenuse is r. So cosine of theta is x over r. And lastly, tan of theta, tan's opposite over adjacent, so from theta, that would be y over x. Now that you remember how to write sine, cos, and tan in terms of x, y, and r, you should remember what the CAST rule tells us about the 3 primary trig ratios in each quadrant. The letters tell you which ratio is positive in its corresponding quadrant. So in quadrant number 2, the sine ratio is positive, which means cos and tan are negative. Since the sine ratio is written in terms of the y-coordinate divided by the radius, the sine ratio will be positive wherever y-coordinates are positive, which is in quadrant 1 and 2. And it'll be negative wherever y-coordinates are negative, which would be 3 and 4. Notice in 3 and 4, only tan and cos are positive. And you can apply that same reasoning to help you understand why CAST rule works for all 3 of these ratios. The other thing you need to remember is what if that circle that the terminal arm is rotating around, right? The terminal arm is rotating around a circle. What if that circle has a radius of 1? We call that circle a unit circle because it has a radius of 1 unit. And if that radius is 1, it simplifies the sine, cos, and tan ratios very easily. So if theta is our angle in there, sine of theta would be opposite over hypotenuse, which is just y over 1, which is just y. For the same reasoning, cos of theta would just be x, and tan of theta would be y over x. So what this should reveal to you is, if we know the xy point of where we intersect the unit circle, the x-coordinate tells us the cosine ratio, and the y-coordinate tells us the sine ratio of the angle theta. And we would know the x and y coordinates of this circle if we were to rotate either 0, 90, 180, 270, or 360 degrees. Then we would know the x and y coordinates exactly, so it would be easy to write the sine, cos, or tan ratios. With all of that knowledge, let's start to learn how we can find certain angles that have a given trig ratio. This first little sentence here explains what I just told you about if we know the x-coordinate of where we intersect the unit circle, then we know the cosine ratio, and the y-coordinate is equal to the sine ratio. Notice, in this diagram that we have over here, if you were to rotate either 45 degrees or 135 degrees, if we zoom in on this, you would notice that both of those terminal arms intersect the unit circle at the exact same y-coordinate. The y-coordinate is root 2 over 2 for both of them. So because they have the same y-coordinate, and we know that the y-coordinate is equal to the sine ratio, that would tell me that both 45 and 135 have the exact same sine ratio. They both have a sine ratio of root 2 over 2. So let's fill in that information. Notice 45 and 135 have the same y-coordinate. Since the angles fall in quadrants 1 and 2 respectively, they will have the exact same y-coordinate. Right? Based on CAST rule, I know that in quadrant 2 and 1, the sine ratio is positive in both of those, and that's because the y-coordinates are positive. So rotating 45 or 135 will get you to the same y-coordinate, meaning it'll be the same sine ratio. So sine of 135 is equal to sine of 45 degrees. They're both equal to each other. They're both equal to root 2 over 2. The next thing we need to talk about is the x-coordinates of those points. The x-coordinates, if we look at those x-coordinates, when we rotate 135, we get negative root 2 over 2. When we rotate 45, we get positive root 2 over 2. So it says the x-coordinates have the same absolute value, but they have opposite signs. So how we could communicate that, we could say that cos of 135 is equal to the negative of cosine of 45. That's the relationship between the cosine ratio for those two angles. And based on Cast's rule, you would know that in quadrant number 2, since only sine is positive, cosine is going to have to be negative. So cosine of 135 is going to be negative. The important takeaway from this is that there are going to be two angles between 0 and 360 that have the exact same primary trig ratio. So using reference angles and the Cast rule, you'll be able to make sure you find both possible angles between 0 and 360 that have the same trig ratio. And that's another thing I should mention. Notice 135 and 45. Look at the reference angle for both of those. Remember, the reference angle is the angle between the terminal arm and the closest x-axis. It's 45 for 135 degrees. And of course, for 45 degrees, the reference angle is also 45 degrees. Because these reference angles are the same, that's what makes them go the same distance above the y-axis on either side, making them have the same y-coordinate, which makes them have the exact same sine ratio. So hopefully you get all of that connection, and let's use all of that understanding to solve a couple trig equations. Example 1 says solve the following equations for theta between 0 and 360. Round answers to the nearest tenth of a degree. So we want to figure out what angle or angles have a sine ratio of negative 0.7. Let me start by setting up this Cartesian grid. I'll label the initial arm 0 degrees, and then as I rotate counterclockwise, I'll label at 90-degree intervals. I'll also label the Cast rule, and now I'm going to try and figure out where are my two answers going to be. There are going to be two angles that have this exact sine ratio. If the sine ratio is negative, well, where are sine ratios negative? They're negative in quadrant 3 and 4. That's because y-coordinates are negative in those two quadrants. So I know I have to draw a terminal arm in both of those quadrants. And the relationship between those two terminal arms is that they're going to have the exact same reference angle. They're both going to have the same beta, the same reference angle. The reason why I know they're going to have the same reference angle is because they're both going to intersect the unit circle at the exact same y-coordinate so that they have the same sine ratio. Now, how am I going to find the principal angles that get me to both of these terminal arms? The first thing we're going to do is solve for the angle in quadrant number 4. And then we'll do for the one in quadrant 3. We'll get two angles, theta 1, theta 2. Your calculator can give you one of the principal angles. Your calculator, if we want an angle and we know the ratio, we can find the angle by doing inverse sine of the ratio. If you type that on your calculator and making sure you're in degree mode, I got about negative 44.4 degrees. A negative angle means to rotate clockwise from the initial arm. So theta 1 is negative 44.4. And since the negative means go that direction, 44.4, I know that reference angle is 44.4. So I can place that same reference angle in quadrant 3, and that'll help me find my principal angle number 2. But let's be careful. The question says to only find answers between 0 and 360, which negative 44.4 is not between 0 and 360. So I need to find an angle that's coterminal with negative 44.4, but falls within that interval. And I can do that simply just by adding 360 degrees to that angle. That'll give me, if I add 360 from negative 44.4, it brings me right back to the same spot, but allows me to express it as a positive angle. So theta 1, if I add 360, I get 315.6 degrees. Whether you rotate 44.4 that way or 315.6 that way, it's the exact same terminal arm, meaning it has the exact same sine ratio. So there's my first answer to the question. Let me get my second answer, which is the angle of rotation to get to this terminal arm. I noticed that I would go 180 plus the reference angle. So 180 plus 44.4 will tell me angle 2. 180 plus 44.4, I get about 224.4 degrees. You could check both of these answers in the original equation. Because we've rounded, we won't get left side exactly equal to negative 0.7, but it should be very close. So you would just do sine of both of those angles, and it should be very close to negative 0.7. I should also mention there are an infinite number of answers to this equation, but when we're limited to the interval of finding answers only between 0 and 360, you're only going to find two answers. Let's try and solve part B, which says tan theta equals 2.1. Let me set up the Cartesian grid quickly again. This time I have a tan ratio that's positive. So where are tan ratios positive? In quadrant 3 and in quadrant 1. So I know I'll get answers in both of those quadrants. So I'll draw a terminal arm in quadrant 1 and 3. And I know those terminal arms are going to have the exact same reference angle. That's what's going to allow them to have the same tan ratio. So I'll place the same reference angle beta in both quadrants. And I'll label the angle in quadrant 1 my first answer, and in quadrant 3 my second answer. And my goal is to try and figure out the principal angle to get to both angle 1 and the terminal arm formed by angle 2. Your calculator can always give you one of the principal angles that satisfy the original equation. The calculator will always give you the smallest absolute value answer. So what's smaller, angle 1 or angle 2? Angle 1 is definitely smaller, so the calculator will give me angle 1. And I can get it by doing inverse tan of the ratio 2.1. When I do that, the calculator gives me the angle that has that tan ratio. And I get about 64.5 degrees. Now the answer the calculator gives you is always the principal angle, the angle from the initial arm to the terminal arm. In quadrant 1, that principal angle is also equal to the reference angle. So the reference angle I know is equal to 64.5. I can place that 64.5 as a reference angle in quadrant 3, and then calculate angle 2 by going 180 plus that 64.5. So angle 2, 180 plus 64.5. Angle 2 is about 244.5 degrees. So those are the two angles that have a tan ratio of 2.1. You can check them. You'll get answers very close to 2.1, but we've rounded, so they'll be a bit off. Let me actually show you an alternate way to get these answers. Let's specifically look at the first one, part A. Instead of getting the first principal angle just by getting your calculator to do inverse sine of the ratio that is given in the question, when the ratio is negative, what we can do instead is you could do inverse sine of the absolute value of that ratio, so just a positive 0.7. But doing that will give you the reference angle. So it'll give you the reference angle that you'll then have to place in the proper two quadrants. So you could always do that. You could always just do the inverse trig ratio of the absolute value of whatever ratio the equation is equal to. But no, that's just going to be the reference angle, not the principal angle. If you were to do that for this question, you would get about 44.4 degrees. And then you would place that reference angle in quadrant 3 and 4, because we know we want the sine ratio to be negative, and it's negative in 3 and 4. And then you can use that reference angle to calculate both of these principal angles. So that's just an alternate method for these questions. Let's move on to example 2. It says the point negative 719 lies on a terminal arm. Let me just roughly plot where negative 719 would be. And it says it's on a terminal arm, so let me draw a terminal arm that goes through that point. And I'm going to connect it down to the x-axis to make a right angle triangle. In that right angle triangle, I would be able to label a couple sides of this triangle. If I'm going to get to this point, negative 719, I would have to go 7 in that direction and then 19 in that direction. So I can label the side lengths of this triangle 7 and 19. Sometimes I've seen people label that side length negative 7. To me, labeling a length as negative doesn't make sense. So what I like to do instead is just remind myself of the cast rule, and then use that to help me remember that in this quadrant, only sine is going to be positive. So if I'm writing a cos or a tan ratio, I would have to make it negative. Now, if I were to think about the angle that goes from the initial arm to that terminal arm, that's angle theta. That's what we call the principal angle. The acute angle between the terminal arm and the closest x-axis, that's our reference angle. That's angle beta. This question wants us to find the principal angle and the reference angle for this terminal arm that goes through that point, negative 719. Well, in this triangle that I created, it's a right angle triangle. From the reference angle, I'm going to label opposite, adjacent, hypotenuse. I know the opposite and the adjacent side, so a tan ratio would allow me to solve for this angle beta. From that triangle, I know that tan of beta, tan is opposite over adjacent, so that would be 19 divided by 7. So tan of beta is 19 over 7. I could get that reference angle beta by doing inverse tan of 19 over 7. And that's about 70 degrees. Now 70 degrees, if you were to rotate 70 degrees, that would land you in quadrant number 1. But our terminal arm is in quadrant number 2. So this 70 is just the reference angle. That's not the principal angle. We need to use the reference angle to help us calculate the principal angle. Let me just quickly label the angles on the Cartesian grid to help us be able to solve for the principal angle. To get the principal angle, notice it is not a full 180, it's beta less than 180. So to calculate the principal angle, theta, it's equal to 180 minus the reference angle. So in this question, it's 180 minus 70, so the principal angle is 110 degrees. So there are two answers, both the reference angle and the principal angle, and we have a diagram which clearly represents these answers. Example 3 says, the point 511 lies on the terminal arm of angle theta. So let me roughly draw where the point 511 would be. That's on a terminal arm. I'll connect it down to the x-axis to make my right triangle. And to get to this point 511, I would go 5 that way and 11 that way, so I can label those side lengths 5 and 11. The question wants me to determine the exact value of the radius. So if we imagine that there's a circle that the terminal arm's rotating around, this side length right here is the radius. I can solve for that side length. I'll call it r. I can solve for r by doing Pythagorean theorem. Pythagorean theorem tells me that the sum of the squares of the shorter two sides of the right triangle equals the square of the longer side. That would mean that 5 squared plus 11 squared is equal to r squared. That would mean that r squared is equal to 146, so r would be the square root of that. So in my diagram, I'll indicate that r equals root 146. Let me add some labels to the Cartesian grid. And now I should be able to write the primary trig ratios for angle theta using all the side lengths of this triangle. From angle theta, let me label the opposite, adjacent, and hypotenuse. And then using my knowledge of SOHCAHTOA, I'll write all three primary trig ratios for angle theta. Sine of theta would be opposite over hypotenuse, which is 11 over root 146. I could rationalize that answer by multiplying top and bottom by root 146, and I would have 11 root 146 over 146. Cosine of theta would be adjacent over hypotenuse, so 5 over root 146, which could also be rationalized. And tan of theta is opposite over adjacent, which is equal to just 11 over 5. So there's the three primary trig ratios for angle theta. The question then says to actually calculate theta. If I want to calculate theta, because we are in quadrant number 1 where all ratios are positive, this should be easy to calculate. I can actually just use any three of these ratios that I know are true and calculate theta by doing inverse sine, cos, or tan of any of the ratios. I'll use the tan ratio. I know that angle theta would just be equal to inverse tan of 11 over 5. Now, there are two angles between 0 and 360 that have this tan ratio. There would be another one in quadrant number 3, because tan's also positive there. But the calculator is going to give me the smaller answer, so it's going to give me the answer in quadrant 1, which is the one that I want. And I get theta is about 65.6 degrees. There you go. I think we've answered everything for that question. Let's do one more question in this lesson. It says, solve the following equation. 3 cos theta plus 1 equals 0, and only find the answers between 0 and 360. Let me start by isolating the cos theta in the equation by moving the 1 and 3 to the other side, which would give me cos theta equals -1/3. If I label my Cartesian grid, I can figure out in which two quadrants will I be able to get a cosine ratio of -1/3. Well, cosine is negative in quadrant 2 and 3. So there will be an angle in both of those quadrants which has that cosine ratio of -1/3. I'll draw a terminal arm in both those quadrants, and what I know about those terminal arms is they're going to have the exact same reference angle. Having the same reference angle is what allows those two terminal arms to intersect the unit circle at the exact same x-coordinate, which is what gives it the same cos ratio. So we have two options here. We could get the first answer, which is the angle from initial arm all the way to the terminal arm in a counterclockwise direction, by doing inverse cos of -1/3, and the calculator will give me the principal angle. Or I can do inverse cos of the absolute value of this, and the calculator will give me the reference angle. I think I'm going to do it this way for now. Maybe I'll show you the other way after. If I evaluate this, I get 109.5 approximately. That means to get from here to here, it's 109.5 degrees. So that is one of the answers to the question. That is one of the principal angles. To get the angle that goes to the second terminal arm, I'm going to have to know what was the reference angle from the first answer. To get that reference angle, I could just do 180 minus 109.5. And that would tell me that the reference angle, 180 minus 109.5, that is about 70.5 degrees. So I can place that reference angle in both those quadrants. And that would allow me to easily calculate my second principal angle. I know it goes past 180 by 70.5 degrees. So I would do 180 plus 70.5 degrees, which means my second principal angle is 250.5 degrees. So there are my two answers to this question. You could take both of those answers, sub them in for theta into the original equation, and it should make it true. And like I said, the alternate way of doing this question, we could have, right at the beginning of the question, we could have found the reference angle, beta, instead of the principal angle, theta, if we had have done inverse cos of the absolute value of the ratio, so of positive a third. And if we had have done that, the calculator would have given you 70.5 degrees. You could have then put that in both of those spots and then calculated both principal angles accordingly. That's the end of the lesson. Hopefully that helped your understanding of how you can solve trig equations. Jensen